Welcome to the External Medicine Podcast. My name is Daniel Belkin, and I'm here with my co-host and brother, Mitch Belkin.
We're both medical students interested in non-traditional ideas and innovation. This podcast is our attempt to explore topics currently on the outskirts of medicine, topics not widely accepted by the mainstream, but that we believe merit a closer look.
This podcast is for educational and entertainment purposes only. We do not endorse any healthcare providers or treatments. Our views do not represent the views of any official organization or institution.
If you'd like to support us, follow us on Twitter at EXMedPod and sign up for our newsletter at externalmedicinepodcast.com/subscribe. All right. This is our last podcast as medical students. In the next few days, we're both going to be graduating, so we will be continuing the podcast as resident physicians.
Do we have any announcements today, Mitch?
One quick announcement. We have a new YouTube channel where we're going to be posting all of our previous episodes. Please consider subscribing to the YouTube channel because that's how people find out about us. You can find us easily by going to youtube.com and just searching for External Medicine Podcast.
All right. Who are we interviewing today?
I feel like you're asking a lot of questions. We're going to be interviewing Dr. Rick Johnson, who we had on previously. He is back because he has a new book called Nature Wants Us to Be Fat. If you haven't listened to that episode number 9, linked in the show notes, definitely check it out. You're going to get a lot of good insight and background into this conversation.
For those of you who need a refresher, Dr. Johnson is a professor of nephrology at the University of Colorado School of Medicine. He is one of the world's leading experts on fructose. His research focuses on the role of fructose and uric acid in obesity, diabetes, hypertension, and kidney disease. He is the author of over 700 academic papers, as well as 3 books for a general audience: The Fat Switch, The Sugar Fix, and most recently, Nature Wants Us to Be Fat.
In this episode, Dr. Johnson tells us about how his views on fructose metabolism have evolved over the past decade. He talks about the thrifty gene hypothesis, how fat is a source of metabolic water, dehydration, and how it stimulates fat production, as well as the relationship between uric acid and bipolar disorder. He also talks about how alcohol-induced liver disease is actually mediated by fructose. And finally, he argues that fructose metabolism is a significant contributor to Alzheimer's disease.
While reading Dr. Johnson's book, I learned some interesting factoids. For instance, lithium, which is a common treatment for bipolar disorder, was historically used to treat gout in the mid-1800s. It was only later noted to decrease mania in bipolar disorder. For a while now, there has been a known association between bipolar disorder and gout. Gout, for anyone who doesn't know, is a disease that is caused by high levels of uric acid. And uric acid is a byproduct of fructose metabolism.
There have been several recent studies showing that allopurinol can be used as an adjuvant therapy in treating bipolar disorder. For anyone unfamiliar with allopurinol, it's a common treatment for gout. These studies have only a mild to moderate effect size, but there is a plausible mechanism of action, which is related to purine accumulation, specifically adenosine. Adenosine is an inhibitory neurotransmitter, which has anticonvulsant as well as mood stabilizing effects. We're going to link to a few papers in the show notes for anyone interested in digging a little deeper. And now we bring you Dr. Rick Johnson. Okay, we're here with Dr. Rick Johnson. Rick, thank you once again for coming back to the External Medicine Podcast. How are you doing?
Wonderful. Nice to see you, Mitch.
Nice to see you
Dan.
too. Before we get started, can you tell us if you have any financial disclosures?
Yes. So I do have equity with Colorado Research Partners. They're making inhibitors for fructose metabolism. I have some stock with XORTX. That's a group that's trying to make uric acid drugs. I also have, I've lectured occasionally for Horizon, and I have this book, Nature Wants Us to Be Fat. which talks a lot about what we're talking about today.
Yeah, we read your latest book. We really enjoyed it.
Thanks.
And just to start off the interview, it's been about a decade since your last book, The Fat Switch, came out. And you go through in Nature Wants Us to Be Fat how your thinking about fructose and metabolic syndrome has evolved. But I was wondering, for people who haven't read your book yet, if you could sort of lay out how your thinking evolved.
Yeah, so when we wrote the book back in 2012, it was really when we realized that fructose was a primary driver of the metabolic syndrome, and we were focused more on dietary sugar and dietary fructose. In the last 10 years, we've realized that it isn't just the fructose that you eat, it's the fructose that you make that is important, and we had a lot of discoveries about what kind of things stimulate fructose production, such as dehydration and high glycemic carbs. We knew a little bit of that back in 2012, but not a lot. And we also realized that this survival pathway that's activated affects things like behavior and could affect things like mental status and the risk for dementia. And we also realized that this also plays a role in cancer. And these were all things that we did not know in 2012. So I felt I should do an update because it really is some significant new stuff.
Yeah. So can you describe what the survival switch is and how this actually supports the thrifty gene hypothesis?
Yes. So the survival switch is what I collectively call, it's a set of behaviors and changes in metabolism that are associated with an improvement in survival in the setting where food is not available. So it's like a switch that animals will put on to help prepare them, particularly to prepare them for times when there's no food. And so it involves stimulating hunger and thirst, and then foraging. And the actual foraging response, where you go into a new environment trying to find food, and it requires a set of behavioral adaptation that is actually part of this survival response. So foraging, hunger, thirst, and then the ability to increase your fat stores. In order to do that, you have to alter how you regulate weight. Normally, we regulate weight very tightly, but in this case, it makes you hungry, so you eat more than you should, and you also reduce your resting energy metabolism. So when you're at rest, your metabolism decreases, but actually when you're foraging, you can maintain your energy and metabolism while you're active. And so, in addition, there's a shift in the metabolism so that you start storing fat. That includes both stimulating the synthesis of fat and blocking the burning of fat. So both of those processes occur. In addition, there's a decrease in oxygen demand because we reduce mitochondrial oxidative phosphorylation, or how the mitochondria work. That you actually inhibit mitochondrial function and stimulate glycolysis. And that what that does is it reduces oxygen needs. So it's another survival mechanism. And then it raises blood pressure to help maintain circulation, helps you hold on to sodium better to help maintain circulation, and it induces insulin resistance so that it tends to raise glucose a little bit and preserve the glucose for the brain, which doesn't require as much insulin as the skeletal muscle does. So it really is very similar to metabolic syndrome. Metabolic syndrome has almost all these same features. Storing fat in the liver and in the blood as triglycerides and in the fat stores, becoming insulin resistance, raising your blood pressure, visceral obesity or abdominal obesity. These are all aspects of this. But in addition, this survival switch stimulates systemic inflammation as a kind of a protection against infection. And so that's actually part of the metabolic syndrome too. So the metabolic syndrome is actually just activating the survival switch, but there's more to the survival switch than we classically know about when we see someone with metabolic syndrome. There's actually effects on behavior and other things as part of this complex. And the relationship to the thrifty gene is the fact that this survival pathway is used by animals to protect themselves during periods of famine or food shortage, like a bear preparing for hibernation or a bird preparing to migrate a long distance. And so you can activate this pathway to help you survive famines. And it looks like there was times in our past where there were famines that were long, very, very long, and led to near extinction of our species. There's at least two times we know this happened. And it looks like this switch was utilized during that time. And actually there were mutations that occurred that made us more sensitive to this switch. And so what happened is we became very sensitive to being able to activate this switch. And it's part of why we survived and why we've done so well over the millions of years. And then what, unfortunately, the switch is primarily triggered by fructose, which is, a sugar that's in fruit and honey, but it's also in table sugar. So then we have this bad thing happen when we start eating huge amounts of sugar, and we were already sensitive to sugar because of these genetic mutations we had. Then the consequence was that we are very, very susceptible to developing obesity and metabolic syndrome and insulin resistance, which goes to diabetes, and elevated blood pressure, which goes to hypertension and so forth. So it really is a thrifty gene. Just for those who don't know, the thrifty gene hypothesis was proposed like 60 years ago by a genetic, one of the first geneticists that was kind of an epidemiologic geneticist, James Neal. He was out of University of Michigan. He was an anthropologist, but he did some of these early genetic studies. And he came up with the idea that perhaps we had acquired a gene or had a mutation in a gene that made us survive famines well in the past, but now in a time of plenty could increase our risk for obesity and diabetes. So that was the thrifty gene hypothesis. People didn't believe it for a long time, but we've more or less shown that it is true, and that there's at least two thrifty genes. They're not the acquisition of a new gene. They're actually mutations that got rid of two genes. But because of that, we're especially sensitive to sugar.
So one thing that you said has changed from the publication of your last book to this book is really focusing in on endogenous fructose, the endogenous fructose metabolism pathways, and how that plays a larger role in not only metabolic syndrome, but this whole fructose pathway. My question is, how do dehydration and high glycemic carbs lead to endogenous fructose production?
Yes. So the first question is, how is fructose made in the body? And it turns out that we make fructose only one way. There's only one way humans can make fructose, and that's called the Polyol Pathway. And there is an enzyme, a set of enzymes that can convert glucose to fructose. So glucose is the main fuel in our blood, of course, circulates, with concentrations around 80 to 100 milligrams per deciliter. When blood glucose becomes elevated, like after a high glycemic meal, if you eat like potatoes or starch or rice, what happens is the glucose goes up from like a normal level. It will go up transiently to like 120, 140, or in that range. And when that happens, it triggers the production of an enzyme that converts some of the glucose to fructose. So this enzyme can be triggered, and we all learned about it in medical school because this enzyme system is called the Polyol Pathway, and it's involved in diabetes because diabetes is the classic disease where blood glucose is high. And so it was known for a long time that in diabetes, there's this enzyme system called the Polyol Pathway that can convert glucose to sorbitol and then to fructose. But most of the emphasis in the medical textbooks have been on the accumulation of sorbitol. And so people were saying, sorbitol is bad because it can be associated with cataracts and so forth in diabetics. But sorbitol can be further broken down to fructose in the body. And this is how fructose is made. And people who are diabetic, you can measure fructose in their blood and in their urine, even when they're not eating any fructose. And you can show that actually everybody has some fructose in their blood, but it's higher in people with diabetes who have high blood glucose. And that's because the high blood glucose activates this pathway to convert the glucose to fructose. Part of that is through its raising the osmolality of blood. So when the osmolality goes up, the concentrate of total solutes goes up. Like if your blood glucose goes up to like 200 or something, that will trigger an increase in serum osmolality that will cause an increase in serum osmolality that triggers the production of this enzyme. So what happens is we knew for a long time that diabetes could make fructose. And in fact, we were doing studies to see how much of diabetic complications are due to fructose production. And we found, to our amazement, that diabetic kidney disease and a lot of, especially diabetic kidney disease, which is what we studied, is part of that is driven by the fructose that's produced when you become diabetic. And if you block fructose metabolism, we could improve diabetic kidney disease. So we knew that fructose was involved in diabetes. Where we got the big insight came when we were talking about, the fact that some people are getting fat without eating sugar. And, it was clear to me, I was talking to people and they would say, when I cut out sugar, I lost a lot of weight. But some people I talked to said, when I cut out sugar and high fructose corn syrup, I still find that I have trouble losing weight. And it wasn't until I reduced all my carbs that did it. And so we knew that, it was likely that there was something else besides dietary fructose that was important. And, I knew French fries, which don't have a lot of fructose, they can't be good, They taste good, but they can't be so good for you. And so we had this insight. Miguel Lanaspo, who was my fellow at the time, said to me, he had been studying the Polyol Pathway previously. And he said, isn't it possible that when you eat high glycemic carbs, that transient rise in glucose might be enough to trigger fructose production? And we knew that the liver was really a key site. And so when you eat food, the nutrients enter the portal vein and they perfuse the liver. They go through the liver before they even hit the bloodstream. So the glucose levels in the liver might even be higher than the blood glucose levels. And, because the liver actually can filter out and remove some of that fructose or glucose when you eat a high glycemic food. So what we did is we gave glucose to animals, and we found that fructose was being produced in the liver in response to giving glucose. And so we had activated this endogenous pathway. And then we found that if we blocked fructose metabolism, the animals still gained a little weight. They ate all the glucose and they still gained more weight than a normal animal. So they did get a little bit of fat, but they were completely protected from insulin resistance and fatty liver. And they had and they were less fat than those that were metabolizing the fructose they made. So then we realized that high glycemic carbs are causing obesity and metabolic syndrome in part by the conversion of glucose to fructose. And actually, it's the major part. And then what we did is we gave soft drinks to animals, and soft drinks contain high fructose corn syrup. So there's both fructose and glucose in it. And some people were thinking that the metabolic syndrome was due to the glucose because the glucose stimulates insulin. But what happened was when we gave the high fructose corn syrup to our mice, they became very, very fat. But when we gave it to mice that couldn't metabolize fructose, they were completely protected, even though they got all this glucose, and they were still making a lot of insulin in response to it. So we know that the endogenous fructose pathway, as well as dietary fructose, was really important. And so we then said, okay, well, this explains why carb restriction is so good. This explains why, when you restrict carbs, you can eat all the fat you want, because although fat's very high calories, if you block the switch and you maintain your ability to regulate weight, then you're just going to regulate your weight fairly well with the fat. And so you're not going to gain weight with fat. But if you take carbs plus fat, then you're going to really gain weight, because the carbs are going to make you hungry and give you leptin resistance so that you're going to gain weight. And then the fat just gives you a lot of calories in addition to the carbs and protein. So the great part was we could explain this whole story of low carb diets and why they're so good. We could explain, why the paleo diet and, some of these diets look like they work well. So that was good. And then, Mitch, what happened was we had another big insight. And I think this one actually is the most important discovery that we talk about in the book. And that is that everyone was thinking about, so even me, I was thinking about fat as a source of energy and how important, there was all these insights that fat can be good. We learned about this from the survival response. We could see how fat could help these animals. And then I started wondering about water, and I realized that fat can also produce water. It isn't that fat contains water, but when you burn fat, you generate water, water and CO2. And so the water is actually generated from the burning of the fat. And it's got a name. It's called metabolic water. And people have known about it for, hundreds of years, I think. But, a lot of biologists knew that metabolic water is really important. And animals in the desert, like the camel, and a lot of these animals carry a lot of extra fat. And there's these fat-tailed jerboas and little mice. They have these fat tails in the desert because they want to. That's a place to store water. I mean, it doesn't store water, but by storing fat, they have a water reserve because they can burn the fat and make water. The reason the camel has the hump and it's not all over its body is it doesn't want to insulate itself, because then it would overheat. But it provides that source of metabolic water. It really is their canteen. And then we realized that it was known that whales get about 2/3 of their water from the food they eat, but about 1/3 comes from their fat. And so then we said, okay, well, fat is a source of water. So, and these animals that are living in the desert, they're not eating high glycemic carbs so much. They're not eating sugar. How are they getting fat? And then we thought to ourselves, well, maybe dehydration could be a mechanism to stimulate fat production. And could it be a mechanism for activating the switch? And the reason that we were thinking about this is, that would be a good reason to want to store fat, is if you're getting mildly dehydrated, because that would be a source of water. And at the same time, we knew that dehydration raises serum osmolality, which is what activates this endogenous fructose pathway. So we knew that, when you raise serum osmolality, that this polyol pathway gets activated. And in fact, there are studies showing that the gene actually has a promoter that is activated by osmolarity related response. So it was known that a high osmolality would stimulate the production of the activation of this pathway. And in fact, as a kidney specialist, I really knew it because the kidney concentrates urine by activating this pathway in the kidney, because in the inner part of the kidney, the osmolality is very high, so it activates this pathway and it produces sorbitol, which is the intermediate, and that actually helps to pull water out of the urine. And so when we concentrate the urine, we actually have activated this polyol pathway in the kidney, along with vasopressin, a hormone that helps concentrate the urine. So the concentration of urine when we get dehydrated is a means to hold on to water, and then the urine becomes very dark and yellow and pungent, and so it actually was known that this polyol pathway was produced. Now, interesting, the kidney doesn't actually produce fructose in the inner part of the kidney where it concentrates, because it misses the second enzyme that converts the sorbitol to fructose. But the rest of the body has that enzyme. So when you get dehydrated, you start making fructose elsewhere. So what we did was we took animals and we dehydrated them, and we found that they were making fructose in their liver and their brain when we dehydrated them. And then the question was, okay, could that be responsible for stimulating fat for these desert animals and for animals, marine animals? And so we wanted to know how important that was. So we started investigating a little bit more. And we realized that although you can dehydrate an animal by just taking away its water, there's another trick to making an animal dehydrated, and that is to give it salt. And if you give salt, that also increases the serum sodium concentration in the blood, which raises this osmolarity, and it would also activate fructose production. And so what we did is we gave salt to animals, to salty food, and actually we put salt in the drinking water initially. But when we did that, the animals started to make fructose. And the incredible thing was the first month or two, they were eating more, but they really weren't gaining weight. They were still regulating their weight. So they just were more active, and so they maintained their weight. And then around the third month, suddenly they started gaining weight, and they became leptin resistant, and they activated the whole switch, and they became hugely fat, and it was like unbelievable. And they got insulin resistance and fatty liver and the whole bit. And they were just eating regular chow with salt. And then the animals that where we blocked fructose metabolism, they actually did not gain weight. They stayed lean and mean, even though they were eating all that salt. And what was even more exciting was the salt-treated animals got their blood pressure went up. They got left ventricular hypertrophy, which is a response to hypertension, and we could block that in the animals that were where we blocked the fructose. So then we realized that fructose is very central to how salt works, and when you eat salt, that the way salt raises blood pressure is probably, at least initially, is driven by this fructose pathway. And so what we did to look at that is we took people and we decided to give them salty soup. And soup is great because you can, add salt to it, and you can't tell how much salt is in the soup. So you can make a salty soup. And then we gave it with or without water. So what we wanted to do was to see if it was the salt that raised blood pressure or the osmolarity that did. So when we gave a lot of salt in the soup, the serum sodium went up, and the blood pressure went up, and we could see that they were activating the switch with the, various tests. And then if we gave the salt, same amount of salt with water, the blood pressure didn't go up and they didn't activate this switch. And so we knew that the activation of the switch is sort of a dehydration response to try to store fat. And that salt, when you eat salty food, you're actually setting yourself up to be mildly dehydrated. And this actually over time will stimulate fat production. So then we knew that dehydration was linked with, and salt intake could be another cause of obesity. And then we started looking at people who are overweight, and we found that there was a literature out there showing that if you eat high salty foods, that you're at increased risk for obesity and diabetes, not just sugar, but there's 7 to 10 studies that had done this. And then on top of that, this hormone called vasopressin, which goes up in dehydrated states, is high in almost everybody with obesity. And there's a wonderful group of investigators that have been studying hydration and obesity. And it turns out that people with obesity are almost always, they're very commonly dehydrated. They're very commonly on a high salt diet. There's some studies show that they're between 2 and 8 times more dehydrated than a lean person, depending upon which type of test you use for dehydration. And so it's pretty remarkable. And when I talk to my friends that were, salt experts, they say, oh yeah, everybody is overweight. They all are on a high salt diet. It's well known. But it's not well known in the literature. It's well known to them because they've been managing these patients for years. So what I loved about this story was that it kind of opened the door to a whole new pathway of obesity. Because when you go to diet clinics and so forth, they usually don't talk about salt. They talk about carbs and protein and fat and exercise. They don't really, salt's not really a big part of the discussion. And if they do talk about salt, they're kind of referring to blood pressure. But actually, these studies show that it was a lot that, that salt was a culprit, like sugar. Sugar is the fast way to go. High glycemic carbs are fast because they make sugar right away. But the salt pathway seems to take a longer time, but it might be just as important. So I can keep going on the salt story because there's more to it. But I think then we started thinking, well, why do animals like salt licks? Why do deer go to salt licks? And then we go, well, actually the deer really eats very kind of poor quality food. I mean, there's not a lot of calories in the grass and stuff that they eat. And so, having a system that could kind of boost it by generating fructose in your body, that would be a great thing if you were eating kind of nutritionally low, calorically low foods. And then we found that there were some papers that actually show that people will give salt to animals to help them grow faster and to become bigger. And it's actually a practice that's sometimes used by people in the different kinds of food industry. And so maybe there's a story there that can be further, figured out.
So one thing that causes dehydration is known to cause dehydration is alcohol. And one interesting thing that you talk about in your book is how alcohol-induced liver disease seems to be caused by fructose. Can you talk about some of the evidence that you present for that?
Yes, I can. So a number of years ago, we realized when we started figuring out this pathway, we realized that it could be activated in a variety of systems. And now it's been shown, and osmolarity is one of the main systems. And it turns out there are other ways to do it too. But and when you drink alcohol, I'm back in the days when I was an intern. Sometimes we would look for what's called an osmolar gap as a way of measuring alcohol for people in the emergency room. Because when you drink alcohol, you raise your osmolality. Now, of course, we just measure ethanol levels very quickly. But so it was known that alcohol could raise the osmolality in the blood, and it should do it in the liver too. So we thought to ourselves, could alcohol be producing fructose? And I actually knew that, we had found that fructose was like the major cause of non-alcoholic fatty liver disease. And we actually were involved in the very first paper showing this strong relationship of soft drinks and high fructose corn syrup with the development of fatty liver. And now there's so many studies that show that fructose is a major cause of fatty liver. And in some cases, that fatty liver can progress to cirrhosis and to chronic fibrosis and progressive liver disease. And non-alcoholic fatty liver disease is now one of the major causes for liver transplantation. But interestingly, alcoholic liver disease is very, very similar in histology. It's also very, very similar in the biochemistry. And when you look in the livers, you find high uric acid in both groups. You find evidence for, this dysfunction of the mitochondria. All the same things that you see with the survival switch, you can show in the fatty livers of both alcohol fatty liver as well as in non-alcoholic fatty liver. So we thought to ourselves, is it possible that the liver disease from alcohol is not from the alcohol itself, but from alcohol triggering the production of fructose? And, oftentimes people who drink alcohol are drinking sugar with it. They make drinks, like the Mai Tai and the Pina Colada and all these things, and rum, which is, is very sweet. And so there are all these drinks that have sugar with it too. Could that combination really be severe in the liver because of that? So the first thing we did was we just gave alcohol with sugar, and we found that when you give sugar and alcohol, or fructose and alcohol together, you really can make the liver disease really bad very quickly. And they potentiate. And when you put sugar in the water with the alcohol, the animals will drink a lot more alcohol. And so they kind of encourage each other. But that wasn't so surprising. But then what we did is we gave alcohol without sugar, and we looked in the livers, and we found high amounts of fructose. And boom, and around the same, we actually were a little bit before another group, but another group published their paper before us. And they found that as well, that people who, even in humans, drinking a lot of alcohol, that if you do a liver biopsy, you can show high fructose, and you can show that the Polyol Pathway, this enzyme system that converts glucose to fructose, is active in alcoholic livers. And you can show it, and you can show that fructose is there. And we had the mice that couldn't metabolize fructose. And so what we did is we gave them alcohol for a long time, months and months and months. And the control animals developed fatty liver and pretty bad fatty liver. And our animals did not get liver disease at all. They were completely protected. Now our paper has been under revision. It's not published yet, but we've been funded on this from the NIH, and it should come out soon. And it's clear that alcoholic liver disease is a fructose disorder. And so that's really important. Now, one of the things I've noticed as a clinician, is that when I see my patients that have alcoholism and liver disease, and they're being admitted, that many of them, when they stop drinking alcohol, will want sugar. And when I go into their room, I'll see cans of soft drinks and stuff on their tray. And I do think clinically, when we're managing patients with liver disease, we should recognize that sugar is another mechanism for causing liver disease and fatty liver. I do think that we should be careful and restrict soft drinks and so forth to our patients with alcoholic liver disease. So anyway, the other side of it was that we had another surprise when we found a long time ago that when we blocked fructose metabolism, that animals reduced their intake of sugar. And they particularly would drink fructose almost kind of like water. If you give them fructose versus water, they'll drink the same amount. When you give sugar, because it has glucose in it, and glucose, animals do like glucose, they'll drink more sugar water than regular water, but they won't drink it as much as a normal animal. It's like we block their craving of sugar, and we block their craving of fructose. Well, the exciting finding was that the animals that could not metabolize fructose also showed reduced craving for alcohol. And so what happened was we could actually train animals to like alcohol and to push a lever to get their alcohol. But when we give them like an inhibitor to block fructose metabolism, we reduce their alcohol intake like by 50% or more. And so we're funded by the National Institute of Health to try to develop inhibitors of fructose metabolism to try to block alcoholism. And it's a big goal of mine to try to do that, to see if we can find a way to help people with alcoholism. So this is another area that kind of came out of this research. It's all new since the prior book, and it's been very exciting.
It's very, very interesting. My next question is about something I read in your book that I thought was absolutely fascinating. Apparently, even in the mid-1800s, it was known that bipolar disorder was associated with gout. What exactly is the relationship between high uric acid levels and bipolar disease? And do we know if using agents like allopurinol to lower uric acid levels, if that has any effect on patients with bipolar disease?
Yeah, so it was noted when people started measuring uric acid, it was noted that people with high uric acid as well as people with gout could be bipolar. And in fact, so that association was known for a long time. And also, there was the substance lithium was used initially to help remove uric acid because it solubilizes uric acid. So lithium was being given originally as an agent for uric acid, and then it was discovered that it helped people with bipolar disease. And so, kind of set up this whole question of, what is the relationship? And one of the things that came out from that was that a number of people did clinical trials of giving allopurinol to see if it might improve bipolar disease. And they were thinking that it might be affecting adenine metabolism more than uric acid, but there are a number of double-blind trials, all small trials that did show part benefit. And they're in the last a partial benefit or additive benefit. So, there are studies out there that really it's surprising. And I do list those studies, and you can read them, if you want, because I do cite them. The other thing is that there have been some studies that have found high fructose levels in the brain of patients with bipolar disease. And so the bipolar disease is sort of an interesting area that needs more study, but it looks like it could be related to the fructose pathway, and that it might involve endogenous production of fructose in the brain. So the other disease that's very much linked with this is attention deficit hyperactivity disorder, or ADHD. And also in that condition, there really seems to be linkage with sugar intake. And, for a long time, it was challenged because there were these studies in the 80s where you could trigger some ADHD type behavior with, you could see it in the group that got the artificial sugars as well as in the group that got sugar. But now we know that artificial sugars can have some issues themselves, and the proper studies really weren't done. But I think that there's a fair amount of evidence to suggest that ADHD is also linked with sugar metabolism and fructose metabolism. So these two, one of the things about ADHD is that it's sort of related to the foraging response. And when you're foraging, you have to move rapidly through an environment. So you have to be a little hyperactive. You have to get out there and look around and try to find the food as quickly as possible. You don't have a lot of time, so you can't deliberate. You can't spend a lot of time thinking about one thing. You have to be constantly looking around, tangentially here, over here, looking around and trying to make sure that you don't see predators, and you have to be potentially aggressive if you see one, or at least be able to defend yourself. And there's a little bit of novelty seeking because you may go into areas where you've never been. And so it's been recently recognized that ADHD has parallels with foraging behavior. And since fructose drives foraging behavior and it works through working on different parts of the brain, it may well be that chronically stimulating those areas can lead to behavioral changes that become more long-standing and can convert from kind of a foraging response to actual behavioral disorders. So it's a really cool new area, I think, for fructose studies.
One thing that most people recognize when they look around society is that metabolic disease seems to be more associated with the old than the young. And something you talk about in your book is how eating fructose over time can lead to a sensitization in the body. And I'm curious if you could expand on that a little bit and maybe talk about if there's any evidence for us being able to desensitize ourselves to fructose.
Yes. So when you eat fructose, you actually, fructose will stimulate its own metabolism. It's like it wants to stimulate its own metabolism. The more sugar you eat, the more fructose you eat, the better you get at absorbing it, the better you get at metabolizing it, and also the better you get at making it. So it also stimulates the making of fructose. So the more sugar exposure you get, the more you become responsive to it. So when you're born, for example, you do not have those enzymes to make fructose in your liver. You're not going to make fructose potatoes. You're going to be safe with French fries initially, because you don't have those enzymes. But the more you get exposed, everything kind of gets turned on, and eventually, a lot of people will have the aldose reductase or the polyol pathway active in their liver. They'll have the transporters to absorb fructose at high level in their gut. They'll metabolize the fructose really fast. We even did a study where we took children that were lean, overweight, or obese, and we found that the obese kids who had fatty liver absorbed and metabolized the fructose that they got much better than the children who were lean. So there is this thing where a teaspoon of sugar is not the same for each kid. So if you have the metabolism turned up, you're going to activate the switch more easily from a spoonful of sugar than if not. And so that as we get older, we become more and more sensitive to the effects of sugar. Now you can stop that, as you say, by just cutting out carbs. If you can cut out high glycemic carbs and, like this severe carb restriction for like 10 days to 2 weeks, it will reboot the system. In animals, you can absolutely show that when you take away the carbs, that the metabolism goes back to normal and the transporters start drifting back to low levels again. So, and it's also known, it's interesting that if you carb restrict for a couple of weeks, your craving for carbs and sugar will also go down. So there's this kind of resetting that's wonderful. And so the beginning of the Atkins diet, for example, is a 2-week severe carb restriction. And I do think that that is something that's very helpful. But there's another mechanism, Dan, by which you can get into trouble. And that is the way the survival switch is activated involves mitochondrial or oxidative stress to the energy factories. So the fructose and the uric acid produced cause oxidative stress to those energy factories. And so that kind of stuns the mitochondria, reduces the ATP production, and then everything recovers fine. But and so like if you're a hibernating animal, no problem. You can do this for several months. The mitochondria are going to recover completely. But if you do this chronically, long-standing, you'll see that the mitochondria start to change. They actually undergo a process called fission, where they become smaller and they kind of they're a lot smaller and they produce a lot less energy. And then what happens is you actually can get a permanent kind of reduction in ADP. And so that's associated with resetting your weight to a higher weight. So now when you diet, even when you do everything right and you cut out the carbs, you cut out all the things you're not activating the switch anymore. You would think you'd go back to your regular weight, but what happens is now your body thinks your regular weight is this higher weight. And so it does all these protective mechanisms to try to bring your weight back up to its regular weight, which it now thinks your regular weight is this higher weight. And so there is a way to beat that, and that's by trying to improve the mitochondria. So if you can actually stimulate mitochondrial growth, you have the potential to actually regain your, it's like blocking, it's like almost like blocking aging. You basically can rejuvenate your mitochondria, slow the aging process, and reset your body weight back to where it was before. And that is a trick. We still haven't, all these people have all these different maneuvers to try to improve mitochondria. There's people saying, resveratrol or these different things. But the thing that's been shown to be the most effective is exercise. And that's the one thing that's been shown in experimental studies, all this stuff, that if you can exercise, there's a certain type of exercise, kind of endurance type exercises, like where you do like 40 minutes on the stationary bike or very fast walk or a slow jog. What you want to do is you want to be in what's called zone 2. And when you're in that type of exercise, you can rejuvenate your mitochondria. And then it's going to be much easier to lose the weight and keep that weight off.
Last question. If you were given, let's say, $100 or $200 million by a philanthropist who was interested in your work, and you could do any experiments that you wanted to, what experiments would you do? What are the big questions that you still have left?
Alzheimer's disease. I want to, we have so much good evidence that Alzheimer's disease is related to fructose metabolism in the brain. I can, in fact, I'm going to write a little editorial on this because the evidence, I think, is very, very strong. I've written one paper on it already, but and I would love to take that money and try to develop a fructose inhibitor that gets into the brain, because it would have to be able to get into the brain, and it would probably cost a fair amount of money to get there. But but if I could make a fructose inhibitor that could get into the brain, I would love to try to block Alzheimer's disease, because the earliest signs of Alzheimer's, it's not the amyloid plaque, it's not the tau protein accumulation. Rather, it's insulin resistance in the brain. And although most of the brain doesn't require insulin, the areas that do are all the areas that are involved in memory and things like that that initiate Alzheimer's. And all those are affected by fructose. Fructose actually causes insulin resistance to those areas of the brain. And then the other early signs of Alzheimer's are these mitochondrial problems and neuroinflammation that are all can be linked to fructose metabolism. And then you can show that the enzymes involved in fructose metabolism are high in Alzheimer's patients. And there's even a study showing that fructose levels are high in the brains of Alzheimer's patients. So to me, and then the risk factors for Alzheimer's like obesity, metabolic syndrome, high salt intake, high glycemic foods, and sugar are all the same things that are associated with activation of the switch. So I think that Alzheimer's disease, I'm going to predict, is actually a fructose disorder due to endogenous fructose production in the brain triggered by these foods, and that we can block this disease if we actually had, if we could invest in this and actually do the studies to try to develop an inhibitor that could block it early. And I think that would be the cat's meow. That would be the cat's meow.
Well, Rick, thank you so much for joining us once again on the External Medicine Podcast. It's always a pleasure to have you here.
Yeah, it's wonderful. Thank you, Mitch. Best to both of you, and continue with your great things you're doing.
All right.
Thank you.
Have a great
Take
meeting.
care.
Great talking.
Yeah.
If you'd like to support us, here are some ways you can help. Subscribe to this podcast wherever you get your podcasts. Leave us a review, preferably a phenomenal review. Visit us at externalmedicinepodcast.com and tell your friends.